involves multiple overlapping subproblems, which leads to redundant computations, right? So to optimize this, we can use memoization. So we are using DP, that is dynamic programming here, which stores previously computed results and avoids recalculating them. So to achieve this, we maintain a 3D memoization array called memo, where memo of I, k, by stores the maximum profit achievable starting from the day I, with k transactions remaining and the current state buy or sell. So we saw in the above approach, there were three parameters that were changing. You see I, k, and buy. Now you see here I is changing and k would also change, right? K becomes k minus 1, and the buying state also changes 0 to 1. So we only take those parameters or those states that are changing and set those as the parameters that would be changing, and basically build this 3D memoization array here. So we store the maximum profit achievable starting from day I with k transactions remaining and the current state buy or sell. Buy is equal to 1 and sell is equal to 0. So by storing results for each unique combination of I, k, buy, we ensure that once the state is already computed, we don't need to recalculate it, right? So this is the utility function int I, k, buy, and now we pass the 3D memoization vector or array, you could say, and the prices vector is also here. So first, let me go to the maximum profit function. We take the prices and the k transactions, and its prices dot size. Now initialize the 3D vector for memoization. So this is the 3D vector, and n plus 1 is the total size of the prices array that we have. That is plus 1. We do for for having one more state. Vector of int k plus 1, right, and vector of int 3 comma minus 1. We are initializing with the 3D vector with minus 1, right. Now this should be vector, right? This is vector. Then start from the first price in buy state. So we just call the same function, and now we are going to this function. So base case is if no transaction left or end of the price list is it has been reached. If k less than 0 or I greater than equal to n, that is prices dot size, return 0. So everything remains the same in the previous code that we saw. We just add a check here. If memo of I, k, buy not equal to minus 1, that is the initial state that we have initialized with minus 1, right? If it is not equal to, if this state is not equal to minus 1, that means it has already been computed. So in order to avoid recomputation, we return a memo of I, k, buy. So we don't need to calculate it again, right? That is to improve the efficiency, right? And we have the same function here that we have. Just we have to replace it with we have to add this parameter of the 3D memo or DP array that we have, and here also we just add the memo, and we store the answer in result. Before returning the result, we store the answer in the 3D vector. Memo of I, k, buy is result, right? So we have just 2 or 3 main things that we have added. First, we initialize the 3D vector for memoization, pass it into the function that we are using here, and we check if it has already been computed. Then there is no need to recompute, just return that, and store the answer in the 3D vector before returning it. So these are the main changes that we do. So time complexity becomes O of n times k, and space also becomes O of n times k. Now another approach is using bottom-up DP, right? So the above solution can be further optimized using iterative dynamic programming approach. Above we did recursive dynamic programming. Now we're doing iterative dynamic programming. So let DP of I, L, buy represent the maximum profit achievable starting from day I, with L transactions remaining and a state indicating whether we can buy or sell. So buy is equal to 1, we are allowed to buy, and 0, we are allowed to sell. Recurrence relation here is buy state is this. So DP of I, L1 is equal to maximum of DP of I plus 1, that is going to the next day. L remains the same, and 0. L is basically the L is the number of transactions remaining, or you could have said K as well, minus prices of I, because we have bought that stock. So prices of I would be reduced from stock, from the total profit we have. DP of I plus 1, that is going to the next day, L and 1, that is changing not changing the buying state, because we are just moving or skipping to the next day. So either this or this. That means either we buy the stock that at the current element, at the current index, or we skip it and go on to the next element. That is the next day stock. And then we have the sell state, that is buy is equal to 0. So here the change is we have the sell state as sell state applicable. That is we will buy this stock. Sorry, we'll sell the stock. Now prices of I plus DP of I plus 1, L minus 1, because now we have sold the stock. So for this we have sold the stock, so we have one less transaction available, so L minus 1. And now we have toggled the buy state to buy is equal to 1. That means now we will be able to buy, since we have already sold the previous stock. Either this or this, and we get the maximum of these two. That is either whichever one is the maximum, we'll get the maximum, since we have to get the maximum profit. And this also means that we are going to the next day. And since we have not sold anything, we'll keep this selling state on. That is, we are setting buy is equal to 0. That means we are allowed to sell, and we are going to the next day, I plus 1. So this iterative approach helps eliminate redundant recursive faults and improves efficiency. So let us see the whole working or the algorithm, how it works. So we maintain a DP 3D DP vector such that DP of I L comma 1 stores the maximum profit for ith day k transaction buy is equal to 1 and sell at buy is equal to 0, right? So this is the array that we have. This is buy and this is sell, right? DPIL1 is buy and DP of IL0 is sell, and this is actually arranged in this format. Since this is a 3D vector, right, we basically have one 2D matrix here, right? This is the buy matrix, and then behind this only we have the sell matrix. So here for this, buy is equal to 1 and this is sell equal to, or sell equal to 1 or buy is equal to 0, right? Since we have buy flag only, so we'll call it buy is equal to 0. So that has been denoted here. That is 1 for buy, and sell we have 0, and this is the array. So we have first built this DP vector, 3D vector. Now we for get the day is equal to 3, I is equal to 3 and transaction 1. Sell state would be DP310. Maximum, we get the same, we apply the formula with the recurrence relation and we fill the table according to that, right? So we keep filling the table and you see that we'll get the answer here, right? So maximum profit would be starting from day 0 with k transactions is DP0, L, 1, right? So DP0 is actually here and L, 1, right? So that's that. And now let us see the code. So in max profit, vector of n prices and k goes in n is prices dot size. If n is equal to 0 or k is equal to 0, return 0. Now DP table to store the maximum profit. DP takes the day, the number of transactions available, and buy or sell. That is buy is equal to 0 or buy is equal to 1. Now we declare the DP vector here, right? So this is these are the sizes mentioned, right? And fill it with 0. So I iterate from the last day to the first. That is, we are following a bottom-up approach now. Since this is also called the tabulation of the bottom-up approach. So for int I is equal to n minus 1, I greater than equal to 0, I minus minus. For int L is equal to 1, L less than equal to k, that is the number of transactions, L plus plus, and this is the number of days. So we are traversing the array from behind. Now we have the buy state. So we follow the same recurrence relation. DP of I L1 is equal to max of DP of I plus 1, that is the next day. And since we are buying it, we toggle it to 0. That means now we'll, in the next iteration, we'll be able to sell the stock. Minus prices of I because we have bought it, and this one is when we are skipping the current day. So we just go to the next day, I plus 1, and we're not changing the buy state. That is, it remains 1. And then we have the sell state, right? So since we have sold it, we get the prices of I profit, and go to the next day and reduce the number of transactions, L minus 1. Since we have already exhausted one transaction, that is, we have bought and sold already, and go and change the buy state to 1. That is, now we will be able to buy another stock later in the array. And this is again going to the next day without changing the sell state. And result is the maximum profit starting from the day 0 with k transactions and in buy state. So that's it.